Thank you. Okay, chapter 2 only has 5 sections, but we're only going to cover 4 because section 2.3 is at the beginning of chapter 5, composite functions. So all we're going to do in this part of the course is chapter 2, these 4 sections. The first 2 sections are going to be in the Dmat homework online. The last 3 will be on the math part. Okay, so when you go online and you go to Dmat, you only see a couple of sections in chapter 2. That's for that part. Then when we do the rest of the chapter, that'll be in your math 13-14, my math lab. Only reason I did that is so it looks better than having everything as one and not getting any grades for the other one. So I did it this way to also give you more exams. So it give you more exams that it'll make your grades better. So, all right. Before we go on, let's discuss functions. I know we talked about it. What is the notation for a function? If I gave you an equation, how would you write that as a function? Or define it, yeah, define them. You can name it whatever you want to. That's an example. The equation part remains the same. The equation part remains the same. The only different now is this, the m part represents the y values. So what we're saying here now is instead of writing y, we're going to have function names. And the beautiful thing is now with functions, I can define what the variable is going to be. Whatever I put inside the parentheses replaces all of the x's inside the equation. So if I give you this now, once I define the function, all I have to do is give you this. What does that -2 mean? X, anywhere I see an X, I put a -2 in its place. So since the function name is M, I go to this function. Here's the equation. Anywhere I see an X, I put whatever's inside the parentheses, and then I work it out. Positive times negative is negative. 3 times 2 is 6. Opposite signs, 6 is bigger, so it's negative. 6 minus 2 is 4. So that's what it's telling us. Didn't we talk about this a little bit once before? Yeah. Yeah, so this is red. The function m of -2 is equal to -4. That's how you would read it. So the function, this is the function name. This is the value of the variable in the equation. And this is your y value, your solution. So there you have the entire path of it. M of 2 is equal to -4. So that's what a function is about. Basically, instead of writing y equals, we're now going to write f of x equals g of x, h of x, m of x. We're going to make up whatever name you want to for the function names. It makes it look more mathematical. So if you want to impress somebody, this looks more impressive than y equals at parties. All right. Now, section 1, chapter 2 is dealing with increasing, decreasing, and piecewise defined functions. Increasing function. What does it mean if I tell you a function is increasing? Okay, it's getting bigger. Yes, but now can you clarify that? What's getting bigger? The numbers, yeah. So basically it's this. Here's an example. This is an example of an increasing function. Because the further it goes to the right, the higher it goes. Is that a positive, negative, zero, undefined slope? What kind of slope is that? Okay, so increasing functions. Yes, because you're reading it left to right. If you do your pen and go this way, it's going up. So it's an increasing. So if you have a positive slope, then you have an increasing function. Now we can see more what it means here. Here's a formal definition of it. As x, the values of x go to infinity, y goes to infinity. So the bigger x gets, the higher y goes. That's an increasing function. We can also say as x goes to infinity, f of x goes to infinity. You have to remember that anytime you see a function, f of x, g, whatever, it's the same thing as y. So any point on this graph, any point that's an x and y is also x, f of x. They all mean the same thing. Okay, this is the basic definition of an increasing function. If we look at it as 2 points, here we have x1 and here we have x2. Here we have y1, which is the same thing as f of x1. This is y2, which is the same thing as f of x2. in a more narrow view of this definition of increasing function, as x1 is less than x2, f of x1 is less than f of x2. Let that sink in. This is by definition what an increasing function is, looking at points. What does this mean? X1 is less than x2. What does that really mean on a number line? Yes, that's a good way of looking at it. Another way of looking at it is x2 is further to the right. X2 is greater than x1. Anything to the right is bigger than anything to the left. So as long as the second point is to the right of the first one, that satisfies that. Now the second one, f of x1 is less than, it's below f of x2. So at x1, we have our first point. At x2, we have our second. Since the first point is lower than the second point, it's an increasing function. How would you define a decreasing function? Okay, so what's the slope going to look like? What's the slope?
So
Yeah, it's like that. But what's the slope? Is it positive, negative, or zero? So it's less than zero. As x goes to infinity, in other words, as we take our pen and move it further to the right towards infinity, y goes to where? As x goes to positive infinity, where does y go? It goes down. Down is negative infinity. Here are the y values. So as x gets bigger, look what happens to each of these points. As x keeps on going, where are these points going? The y values. They're approaching negative infinity. That's what that says. So again, we look at as x goes to infinity, f of x goes to negative infinity. Or as x1 is less than x2, f of x1 is greater than f of x2. So let's say this is x1. Let's say this is x2. Is x1 less than x2? This one?
No.
That's as.
Okay.
Yes, that's. So as x1 is less than x2 because it's to the left. So that satisfies. Let's look at the y values. There's f of x1. It's over here. F of x2 is here. Is f of x, is the y2 higher? Is the y1 higher than y2? Yeah, here's y1 and here's y2. Yeah, so that's, if that happens, then we know we have a decreasing function. Can a function be both increasing and decreasing? You're right and you're wrong. Which one's which? Let's look at this. This is a function. How do we know it's a function?
Was it line test or something?
The vertical line test. Yeah. So if there is a vertical line test, if you could draw a vertical line anywhere on the graph, it only crosses the graph once, then it's a function. And then this, what's this kind of graph called? Parabola, right? Parabola. It's a parabola. Let's say it has a bottom here at x equals 3. And at this point, at 3, -3, we have what's called the vertex. So let's look at this graph. At the vertex, at this point here, what's the slope? Here's the line, the tangent line at the curve. It's a horizontal line. At the vertex. At the vertex, there's the slope at that point is 0. It's a horizontal line. Because of that, what happens to all these points here? What kind of slopes do they have? If these are all slopes going through lines. Well, okay, do your pencil then. What direction is the graph going if I do this? Vertical. Decreasing. Because look at the graph along my pen. It's going further down the pen. So it's decreasing. So on this side, it's decreasing. At the vertex, it's 0. And then when I keep on going this way, what's happening to the graph now? It's increasing. So a function can have all 3 of the types. You can have a horizontal line, a 0 slope. It can have an increasing or decreasing. In other words, the slope here is negative. The slope here is positive. And the slope here is 0. Doesn't that make more sense? If it's negative here and positive here, what's in between negatives and positives? 0. Where there's no slope. It's neither going up or down. So how would you tell me? What is the range? Remember, the range deals with the y values. The domain deals with the x values of a function. So what's the range of my graph? Just -3? To -3, because remember the range deals with the y values. So it says here that y is greater than or equal to -3. Because the lowest they could be is -3, and everything else has to be above there, all the y values. So that's how you tell me the range. The domain. But now the domain, since we have a function that has increasing, decreasing, and zero, I want you to tell me where is it increasing? Where is it decreasing?
I think go in the vertex forward.
So the graph keeps on going this way forever, right? So it starts at negative infinity and goes all the way to where? 3. So it's decreasing from negative infinity to 3. Or x is less than 3, strictly less than 3. Didn't we do the inequalities last week? Yeah, so that's what we talked about last week. Where is it increasing? From 3 to, yeah. So it goes from 3 to positive infinity, or x is strictly greater than 3. You have to be able to tell me in either one of these formats, the interval notation or set notation. Which one's which? What notation is this? Set notation has the inequalities. Interval. Why don't I have brackets on 3? Why is it open?
What's the graph?
It keeps on going, yes. It doesn't stop. But at 3, what's the slope at 3? It's 0. Is it increasing there or is it decreasing? Or neither? Neither. So I can't use 3. 3 is the vertex. At the vertex, it's neither increasing nor decreasing. So you'll always have parentheses on these guys. All right. Let me give you a function, you graph it. Tell me where it's increasing, decreasing, or 0. Okay, so how do we graph this equation? What kind of equation is it? It's, well, we know it's a line. How do we know it's a line? Well, it has no exponents, no special operations, there's no fractions, and x is not on the bottom. Because of that, we know it's a line. Therefore, it's called a linear equation. And it's in what form? Yeah, mx plus b. So how do we graph that? we graph the intercept first. And from the intercept, we follow the slope. It's gotta be a fraction, so it's negative. So I go down 3, -3, so 1, 2, 3, and over 1. Down 3, over 1. And there's my graph. Now you see why you have to stay current when we finish a lecture. Do your homework as fast as possible so you don't forget it. We only talked about this a week and a half ago. So please go start doing your work. Because today also we're going to go through all different types of functions. There are 14 of them. You're going to have to know how their domains, their ranges, their how many intercepts they're going to have, their function, everything about it. So where is it increasing? Nowhere. It's a decreasing graph. Where is it decreasing? At negative infinity to positive infinity. Where is it 0? Nowhere. Okay, I'll give you another one. The function 1 over x minus 2. This is the x-axis. It goes to infinity. It goes to negative infinity. This line here is called the asymptote. Does anybody remember what an asymptote is?
No. I don't remember.
Which it's been what, a couple of years.
Is it when it's opposite?
No. Nope. The asymptote is the value that'll make the function undefined. An asymptote the value that makes a function undefined. An asymptote is basically it's a value you cannot use. So it's a value that makes the function undefined. Okay, what's our asymptote? What number is our asymptote? X where? X equals 2. So our asymptote is at x equals 2. What happens if we plug in that value into our original function?
Oh,
2 minus 2 becomes 0. 1 over 0 is undefined. So the rule is I cannot have 0 on the bottom. So if I give you a fraction and x is on the bottom, just set the bottom equal to 0, and that'll tell you where your asymptote is. That's the line your graph cannot cross. So, and the 1 over x function looks like this. So where is it increasing? Where is it decreasing? And where is it 0? Ah, very good. How do we know it's not increasing anywhere? Well, it was, if we look at the graph, anywhere it goes, it's going further down. Anywhere it goes, it's going further down. So it's a continuously decreasing function. Where is it decreasing? Negative infinity. To 2. And then from where to where? There we go, from here. From 2 to infinity. What symbol goes here? Yep. Since we're dealing with interval notation, we put the U for union. Again, for those of you who missed last week's lecture on the inequalities, it's on sale in the lobby. No, it'll be uploaded for sure. Make sure it's posted tonight. We have to watch that and go through the whole thing. Is it 0 anywhere? It doesn't have, because it's always continuously negative. It doesn't go anywhere. It doesn't, the only place you can have a 0 is if it goes down and then up. It has to go opposite directions both ways. All right, so that's what we're looking at here. So this is what our domain, these are our domains. Since it's always continuously decreasing function, that's where it's decreasing at. Okay, let's look at another fraction function, rational function. One over x plus 1 squared. Nope. You can't, no, you can't distribute it because there's a plus and minus sign. Good thought though, but no. No, because if you square root, you have to square root both sides. You square root the answer also. So remember what I said, if you have a fraction and x on the bottom, what do? Say it equals 0. So we know at x equals, what happens at x equals -1? At x equals -1, the bottom is 0. So this is that's my asymptote. So we know at -1, we have a line that the graph cannot cross. Whenever you have a fraction, set the bottom equal to 0 and solve it. That'll tell you everywhere you cannot have an x-intercept. Now, here's another thing. Can this answer ever be negative? Why? What? Because of the exponent, yes. In other words, if I put -5 as x, -5 plus 1 is -4, and I square it, it becomes +16. So if you have an even exponent, it'll make any number inside there positive. So that means our answer cannot be below the x-axis. Our graph will look like this now.
Oh.
The Atari. Atari. Video games. The Atari video game, the symbol. So where is it increasing? Is the left side or right side? Which one of those are increasing? It can't be both, because look at
No, just left side.
just the left side. And where does it start?
Negative.
So it goes from negative infinity, and where does it stop? -1, very good. And then where is it decreasing? Very good. Easy, and doesn't have a zero anywhere, because the next one's gonna have zeros. Actually, I have a couple of them. I'll show you. Yes.
What did you do to explain?
All this exponent here tells me that I cannot have a negative answer, because the only x I have in my equation is on the bottom and it's squared. So it tells me that no matter what x value I put in there, if I put -5 inside there for x, -5 plus 1 is -4, square becomes +16. So all this thing does is makes all my answers positive. So I know it's above the x-axis. And because of that, since basically the difference between this equation and this one, if I couldn't have negatives, I'd flip this up. Then it would be like that. So how can we get the bottom out of there? We flip it up. Let's look at this now. Let's look at now a cubic function. Actually, let's go through all the functions. And next class, I'll give you the formal sheet, the nicer looking one. So all I did is I cut it in half and made a bunch of cross lines. The first type of function is a constant function. F of x equals some number. There's no x, no x or no variables. It's just a number. So for example, if f of x equaled 2, what would that graph look like? It's a horizontal line going through 2. We know it's horizontal because it can't cross the x-axis because there's no x variables. You can only cross the axis that has a variable in the equation. Since it only has y equals 2, it can only cross the y-axis. So that's a constant function. A linear function. A linear equation can be rewritten in this form. In other words, there's no exponent, there's no fraction, x is not on the bottom, there's no square roots anywhere. So for example, 3x minus 1. We know the y-intercept's at -1. And the slope is up 3, 1, 2, 3, and over 1. There's that graph. And hopefully after this week, you'll have enough information. So I can give you any type of function and you can tell me the basic shape of it, what it's gonna look like. All right, next ones. The next one's a quadratic function. Constant linear quadratic. And here's the basic standard formula for a quadratic function. How do we know it's quadratic? It's quadratic because the biggest exponent is a 2. Once you see an equation that has an exponent of 2, we know it's quadratic. That exponent, since it's the biggest, it's also called, I'm not gonna give those names just yet. It's the power. So for example, if I gave you this equation. Where A, B, and C are coefficients, they're numbers. So in our equation here, what's A? A is in front of x squared. So it's a 1. What's B? Well, is there an x value there? So it'll be 0. What's C is the constant and it's -2. The graph of this thing will look something like this. Ready for the next one? The next one is called a cubic. A cubic equation. The biggest power it has is a 3. Okay, now I didn't want to spoil it earlier. Instead of its power, the biggest power in equation is called the degree. The degree of the equation, okay, it's the largest exponent. It tells us a lot of things. It tells us, well, let me give you this picture first. Cube. That graph looks something like this. So the degree will tell us a couple of things just by looking at it. If the degree is even, we know both ends point the same direction. Either they go up or they go down. If the degree is odd, both ends point different directions. Either one end down to up or the opposite, they flip. So just by looking at the degree, you know the basic shape of the curve now. Also, the degree tells us how many times can we cross the x-axis. If the degree is 3, we can cross it at the most 3 times. If the degree is 2, then 2 times. If the degree is 7, at most we can cross it 7 times. So again, now we know how many times it can cross the x-axis, which direction the ends go. And it also tells us how many vertices we can have. Remember what a vertex is? A vertex. The vertex is the lowest or highest point on a curve. It's where the slope is 0. The vertex is where the slope, it's the point where it changes from going up to start going down, or from going down to start going up. In other words, at the vertex, on one side, you're going to have a positive slope, and the other side, you'll have a negative slope. Always. You have different slopes on both sides. Okay, and we'll go more in this detail later on. So again, the degree tells us what it's going to look like. Irrational. What does rational mean? It means fraction. So for an example of a rational equation is like that. In a rational equation, the right side goes down, and so does the left side. We did that, yeah. Because we had an x plus 2, we know that we have a -2 is our asymptote. Rational. Uh-oh, that was dying up. Rational squared f of x equals 1 over x squared. Because the bottom is squared, that's where the x is, the answer can never be negative. So it can only be positive. It's always above the x-axis, all our answers. The next one's a radical. When we say radicals, we mean this symbol here. That's the radical. So what rules do we know about square roots? Inside there, what can X be? Can X be negative?
No.
No. Can X be zero?
Yeah.
Yeah, square root of 0 is 0. Can X be positive? Okay, so the only thing about it, we can't use negatives. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. 5, 6, 7, 8. Square root of 9 is 3. So this is the graph of a radical function. Square root. X cannot be negative. It can only be, yeah. So inside there, it can only be 0 or greater than 0.
Well, the actual straight line is-
Well, it's not, it's a curve. It's a very slight curve. But what's happening here is the next one, it would be at 16
So you went from 1
to 4
to 4.
to 9 to 16, and that's when it grows up 1. So it keeps on, it's barely increasing going up, but it's still an increasing function. Now a cube root. Whenever you hear the word cube root or square root or fourth root or fifth root, that's what this is talking about, that little number there. It tells us how many times a number has to repeat itself before we can take it out. This is a square root. It's got an invisible 2 there. Why is the square root of 4 2? Because 4 is 2 times 2. It happens twice, so I take it out. 9 is 3 times 3. Yeah, so since it happens 2 times, I take it out. So in this one, cube root of 8. What's 8 made up of? 2 times 2 times 2. So the answer is 2, since it happens 3 times. So that the root tells us how many times it has to repeat itself. Once it does that, we can take it outside the radical. Now, because it's cubic, it's an odd root. It can be negative, it can be positive. So if you have a cube root function, it has a square root side, but then it has the negative side. So far, so good. Absolute value. We talked about these last time as well. What does absolute value tell us? What does it make it, the answer? Always positive, right? Absolute value of 0 is 0. Absolute value of -1 is 1. -2. Absolute value of 1. Absolute value of 2. Yeah, so it keeps on going this way. It's a V. It's a V. It's 2 linear equations. Yeah, so I'm not gonna get into logarithms and exponentials just yet. We'll do that in chapter 5. But the graphs of logarithms and exponentials. The greatest integer. I said, now you understand why I don't like PEMDAS, is because these symbols never appear in PEMDAS. But they exist. It looks like a bracket with a line, extra line inside there. It's the greatest integer. What it does, if I have the numbers 0.1, what's the, basically all I do there is I drop the decimal, so it becomes 0. If I have 0.7, drop the decimal, it becomes 7. I mean, 0.
Oh,
It's called a step function. I'll show you why in a second. From 0, everything up to 1, it stays 0. But once it goes to 1.0, it jumps up. It stays 1 until it gets to 2. Then it jumps up to 2. And so on and so forth.
What's that bracket called?
The greatest integer function. It's called the greatest integer. And likewise with negatives. It works backwards. So you see why you call it a stair step function? It looks just like that. And I promise I won't give you too many of those. Maybe one. If you upset me. Okay, I have 1 over x squared. Okay, this is a good start. 2, 4, 6, 8, 10. There's 10 of them. We'll get to a couple more. We'll do the inequality. I mean the logarithms and exponentials in chapter 5. We have a couple more, but this is the basics of them. These are what we call the library of functions. So everything we do will be following these from now on. Now, remember I told you earlier about if I give you a function. What can you tell me about that graph?
if you go here for,
What's that?
into it for,
Well, okay, this 4 tells us we'll have at most 4 x-intercepts. What else do you know? What do we know about the end behavior? It's called end behavior is the way, what do both ends of the graph point? Since it's even, both ends point same direction. Now, that's all the exponent tells us. It tells us that both ends point the same direction. Whether it's up or down depends on this number. It's called the leading coefficient. Both ends point same direction. Up if the leading coefficient is greater than 0, if it's positive. Down if the leading coefficient is negative, less than 0. There's something else we can tell about this graph of this picture. The constant is always called the y-intercept. That's the only point we know for sure. Another thing, maximum number of vertices. How many vertices can I have? 3. The number of vertices always has to be one less than the number of x-intercepts. Just think of the parabola. It crosses it twice, we have one vertex. So if this number here is, this we typically call n, the degree. The number of vertices is always n minus 1. It's the side, the degree minus 1. So because the leading coefficient is positive and it's an even degree, we know that both ends have to point in the same direction. They're both pointing up. And we know it has to cross the y-axis at 4. The rest of the stuff has to be calculated out. And that's what you're going to do in chapter 4. You're going to find me the equation. You're going to find me all the x-intercepts. You're going to find me the vertices. You're going to find me everything about it in chapter 4. So basically, our graph will look something like this. We know it has both ends have to point the same direction, has to cross through 4, and we'll have at most 4 intercepts. But again, that comes later on. But we will have at least a picture of what it looks like. All right. Now, that does it for section 1. Let's look at section 2. The algebra of functions. When we say algebra, all we're talking about is we can do these binary operators on functions. We can add 2 functions together. We can subtract them. We can divide them. We can multiply them. So the first one. This is the addition of two functions. And what it means, I'll put all four of them first, and then I'll show you what it means. It just tells us how we can solve for these. Whether we could add the two functions together and then take the x, or then find the actual values and then add the answers together. F minus g is the same thing as f of x minus g of x. F times g of x is the same thing as f of x times g of x. And the last one, f over g of x is the same thing as f of x over g of x, where g of x cannot equal 0. It looks complicated right now, but once I give you the example, it'll make more sense. So we're gonna go through all four of these. I'm gonna give you the same two functions for all of them. 3x plus 2, and g of x is 5x. These are our two functions we're going to use. So the first one. The addition one says this. I'm going to use all of them at x equals 3. I mean, for this case, I'm just going to use all of them at x equals 3. So we have it easier to see what we're doing. So the addition formula says this. This is the same thing as that. So far, so good? All I'm doing is setting it up. What this first part tells me to do is I can add the two functions. So f is 3x plus 2 plus 5x. So 3x plus 5x is 8x plus 2. Now x is what? X is 3. So wherever I see an x, I put a 3. Eight times 3 is 24. 24 plus 2 is 26. That's what the first one says. The first one says, I can add the functions together first and then put the value of x in there. Now, the next one says, I can take each one of these. So f is, but now anywhere I see an x, I put a 3. There's the plus sign. And g of x is 5. Bless you, it's supposed to be 3. So anywhere I see an x, it's always going to be a 3. So work it out. 3 times 3 is 9. Plus 2. 9 or 5 times 3 is 15. 9 plus 2 is 11. 11 plus 15 is 26. So that's what it's telling us, is we can either take two functions and treat them both separately and just add the answers together, or add the functions together and then find the answer one time. Let's go ahead and try the minus one, subtraction one. Remember, f of x equals 3x plus 2, and g of x equals 5x. We're saying x equals 3. We're doing f minus g of 3. Again, the left side here, f minus g, it says f is 3x plus 2 minus g is 5x. Combine like terms, 3x minus 5x is negative 2x. X is 3. So now I put 3 in place of x. Negative times positive is negative. 3 times 2 is 6. Negative and positive, 6 is bigger. 6 minus 2 is 4. So the answer is negative 4. Let's do the left side, or the right side. F of x is 3x plus 2. So in place, so I have 3 times 3 plus 2 minus 5 times 3. Very careful is that if this was a larger equation, I have to put it in parentheses. If this was 5x minus 2, I'd have to put a parenthesis on it because this minus sign changes everybody's sign inside there. But since it's only a single term, I'd leave it alone. 3 times 3 is 9 plus 2. 5 times 3 is 15. 9 plus 2 is 11. 11 minus 15. 15 is bigger, so it's negative. 5 minus 11 is 4. What's that? You did something wrong. Because these things have to be right at the same things. Let's try the multiplication one. F times G of 3. F of 3 times G of 3. Three x plus 2 times 5x at 3. Because here I'm multiplying the two functions together first. Now, anybody know how to do this? It's kind of, but this FOIL only works when you have two binomials. This is distributivity. So 5x times 3. So we have 5 times 3 is 15. X times x is x squared. Next one. 5 times 2 is plus, they're both positive. 5 times 2 is 10. X. Unlike addition, when you multiply variables, you change the exponent. If you add and subtract variables, you only change the coefficients. So now we plug in everything. 3 squared plus 10 times 3. What is 3 squared? 9. 10 times 3 is 30. 15 times 9. 9 times 5 is 45. 9 times 1 is 9, plus 4 is 13. 135 plus 30 is 165. Now let's do the right-hand side. Remember, f of x was 3x plus 2. So it's 3 times 3 plus 2 times g of x was 5x times 5 times 3. 3 times 3 is 9 plus 2. 5 times 3 is 15. 9 plus 2 is 11. Yeah, 11 is 10. So 10 times 15 is 150 plus 1 more is 165. Yes, obviously, yeah, the right-hand side is a lot easier. Is you take each function separately and then put the answers together at the end. Much easier. But sometimes it may be easier to combine them first and make them smaller and then put them in there. It'll save you time in the long run. So these are equal. Okay, let's look at division. The functions by name. We're going to try to prove that this is true. As long as g of 3 does not equal to 0. The bottom cannot equal 0. Nothing simplifies. So we just plug them in there. 3 times 3 plus 2. 5 times 3. We don't need parentheses anymore. 9 plus 2 over 15. 11 over 15. And yeah, clearly you see the right-hand side. If you do it separately, it's much easier. Three times 3 plus 2 over 5 times 3. 9 plus 2 over 15. 11 over 15, and they work. So that is the algebra of functions. You can combine them, you could add them, multiply, divide, and subtract them. Section 3 goes one step further, is we can put functions inside functions. It's called composite functions. That will save for chapter 5. What time is it? Almost 2 o'clock. Yeah, I forgot the piecewise defined functions. I'll show you, I'll show you two examples of simple ones, what they mean. A piecewise defined function is just that. We define a function in pieces, in parts.
Did a conference.
Yeah, well, semicolon. A piecewise defined function, it takes one function and it breaks it down into multiple parts. These are the y values. These are the x values. What this thing says is whenever x is strictly less than 1, we'll use this function. Because it's not a set of answers. It just means that this function, because I can have multiple, you can have like 5 or 6 lines on there also. So it just means that all these filter into this one function. So let's look at this. X is less than 1. Okay, always begin at that value there. When x is 1 in this equation, 2 times 1 is 2. What's below 1? 0. 2 times 0, 0. Negative 1, 2 times negative 1 is negative 2. So these points define this first equation. Can I use the value 1 as x? No, it's not in the domain. So I put an open circle there. That's where my line stops. That's where my graph stops. The next one's at 0, 0. The next one's at negative 1, negative 2. It's a line. How do we know it's a line? Because 2x is a linear equation. So there's that graph. Now we know the second one's a line also. So we plot some points there. Start off at 1. When x is 1, 3 times 1 is 3, plus 2 is 5. And x is bigger. Next one's 2. 3 times 2 is 6, plus 2 is 8. 3 times 3 is 9, 11. So for the second equation, I plot these points.
Whoa, how did you get all them numbers? When was it fast?
These are the x values. These are the y values. And for any x bigger than or equal to 1, I use this equation. So when x is 1, do the math.
I got it.
All right, so when x is 1, 2, 3, 4, 5. I put a solid dot there because I can use 1 in that set. When x is 2, 7, 8, it's 8. And it keeps on going that way. So that's what a piecewise defined function looks like. Right, this one here is the second equation. That's the first equation. And you notice I have to put an overlapping of where one ends, where the other begins. That's why I use an open circle. Because I can't use that point. I start the next one up here. Let's try another one, and then we'll call it a day. This one's going to have 3 equations. Yeah, plot these points. Once you have these points, just plot them. And you since you know since they're both linear equations, connect the dots. You have to make sure that the domain, all the x's are taken care of. There's no jumping anywhere. I go from negative infinity to -2, from -2 to 3, and from 3 to positive infinity. All of them have to be allocated. You can't have a blank space. What kind of graph is this going to be? This will be a line. It's a linear equation. So all we need are 2 points there. We'll start off at -2 and go to -3 because it has to be less than -2. When x is -2, what do we have? -2 times -2 is +4. -2 times -2. Negative makes it positive. 2 times 4. When x is -3, +6. So here are our first 2 points for this first line. At -2 is going to be an open or closed circle. Open, because there's no line underneath it. So this one's going to be an open circle and this is going to be a dot. What's this one going to look like?
Well, and it goes,
Wouldn't it be Y?
oh, you're talking about the line.
Yeah, this is the y value of the second part. Let's go start graphing it. Let's start. Nope. There's no x, so there's no slope. You guys are close, but you're shooting all the way around it. So at -2, we're at 4. 1, 2, 3, 4. It's an open circle because I can't use it. At -3, I go up to 6. It's a closed circle. It's a line from there. So that's the first, this is the first equation. Okay, now the second one. At -2, what's the answer going to be? 3. So at -2, it's 3. What's it at -1? Also 3. When x is 0, when x is 1, 2, 3, they're all 3. It's a horizontal line. But when I get to 3, it has to be an open circle. Why is it an open circle at 3? It's not included. It's not included, so I can't use it. Whenever you have a single number, that's a horizontal line. Remember, these are your y values. When x is -2, what's y? 3. When x is 0, what's y? 3. When x is 3, y is 3. Now the next one. When x is 3, we start off with 3. 4 times 3 is 12. Absolute value of 12 is 12. Whoops, I should have done that. Let me make it, forget the 4x. That's going to make it 2 off the graph. Let's leave it as just absolute value of x. So when x is 3, absolute value of 3 is 3. So it's in there. When X is 4, it's 4. So it keeps on going that way. So there's your graph. Basically, it's one graph. It's 3 graphs on one paper. That's why they call it piecewise. Each piece is defined on the same graph. Try your homework. If again, that's why I need you to try your homework. Try it. If it's still complicated, then we'll go over it again. We'll do some examples, more examples. You know what GO stands for?
You know,
Get out.